So because we're thinking about prediction, much of the work that's been done has been using numerical models to look at climate impacts and now extending those to the ecosystem. But as Laurent mentioned, the social parts of the marine system are also extremely important. And in many ways, that's what we care about most at the end is the impact on humans and communities. So we're very happy to have as the keynote speaker for our workshop, Eddie. So a few words about Eddie. He comes from a background of marine biology. He worked first on scallop fisheries, actually, when he did his PhD at the University of Liverpool. And after that, he worked on pelagic fish in Lake Malawi for a couple years, after which, correct me if I'm wrong about any of this, but then he moved as a lecturer in natural resources at the University of East Anglia, where he worked for a number of years before leaving academia and going to work for an NGO, the World Fish Center in Penang, Malaysia, where he worked for a number of years, until he decided to return to academia in 2013, where he's now a professor in the School of Marine and Environmental Affairs at the University of Washington in Seattle. So a lot of experience, and I think I'm sure he's gathered a lot of wisdom along that path, which I think comes through in his papers that are on a range of topics with strong common themes in his work of human rights, food security, and vulnerabilities to climate change. So very excited to have him here as the first speaker to kick off the IMBiZO. And let's welcome Eddie. Hi.
Thank you. Is the microphone okay? Can everyone hear that? Okay, great. I've been invited to talk about the limits of prediction, and there's nothing in Eric's introduction that suggests that that might be a topic that I know anything about. And in fact, I kind of agree with that. Having said that, I work across a number of fields, and questions about what we know and don't know, I think, are common in all scientific disciplines, and indeed in everyday life. I think if you look at, did anyone predict some of the political upheavals we've seen in the last few years? Not that many. There are limits to prediction in all kinds of fields, including that of sort of politics and international affairs. So this is something that confronts us as a group of people who largely work on the premise that by contributing better mechanistic understanding with better parameterized models, we will extend the limits of prediction and be better at predicting the coming storms. So the IMBeR research goal is to understand, quantify, and compare historic and present structure and functioning of linked ocean and human systems in order to predict and project changes. So prediction is at the heart of IMBeR's research goal. And there is also, I'm pleased to see, an emphasis on developing scenarios and options as well. So it's not just about the sort of projections and predictions, but also acknowledging that, again here, the limits of prediction and the requirement to develop scenarios and options for a range of potential projected outcomes. That acknowledges the reality of how difficult it is. Niels Bohr's famous phrase that prediction is difficult, especially about the future. But there is incredible political pressure to predict. Admitting uncertainty, as many of you have found to your costs possibly in dealing with the media on some of the high-profile papers that I know many of you have published. Uncertainty opens up space for skepticism and denial, and more importantly, it justifies inaction in addressing global environmental change. Committing funds to adaptation or justifying costs of mitigation is also easier if there are reliable predictions or projections of the potential benefits of doing so. So there's a strong pressure from the organizations that fund and commission our research to engage in the science of prediction. So what is it that we're trying to predict? I'm going to give just a couple of examples. Future fish stocks from stock recruitment relationships as an example of the kind of prediction that fishery scientists do. and the effects of climate change on the oceans, and subsequently the impacts of those changes on society. And ask the broader questions. And really I see this talk as more about sort of setting the scene for your discussions rather than answering questions. So I'm going to actually conclude with a set of questions. But my starting point questions are we getting better at predicting? And is chasing better predictions a worthwhile goal for IMBeR, for example? And if so, how do we do that? And if not, what else can we do? Just a few kind of definitional concepts, and best illustrated when talking about weather, I think, where a lot of the science of prediction came from weather forecasting and subsequently the understanding of climate variability and climate change. Forecasts are at short-term scales in this seamless suite published by NOAA and used by many others now. Forecasting in terms of minutes, hours, days, and weeks, and based on a good understanding of initial conditions. And we've seen that at play recently in the spate of hurricanes that have hit the Caribbean and the southeast of the US. And even there, with excellent predictive capabilities, it's not always been possible to predict where the rainfall that eventually sort of flooded the city of Houston was going to fall, and what the exact track of the hurricanes were going to be. So, costly evacuation took place in places that weren't hit, and then it wasn't possible always to respond in time in places that were predicted or were not exactly predicted to bear the worst brunt of it. But by and large, at that kind of scale, our models, physical models of the climate system, allow us to make quite good short-range forecasts. And you'll see that the two lines there, the forecast uncertainty, that diverge as you go sort of up the time and space scales. And we can make outlooks and predictions and offer guidance on how to address climate variability, the sort of seasonal forecasts, the advance warnings of upcoming ENSO events, for example, and their likely relative strength. We've seen some utility in those forecasts in recent years. And when it comes to predicting climatic change at the scales of decades, centuries, then we're essentially here talking about scenarios rather than predictions. And I'm going to sort of come back to that a lot later. And our anthropogenic forcing, in particular, comes from a social and economic understanding of how the world works. And that's another theme I'm going to return to later. Starting really simply, and many of you have probably done this, as I have with undergraduates or graduate students, in understanding how complex the behavior of even a simple population relationship can be. This is simply a sort of density-dependent growth projection, a population at time t+1 as a function of the population at time t, simple logistic growth curve. And if you increase the growth rate of that population, the function r, the population begins to oscillate in regular ways. And if you increase it, in this case, with a value beyond, I've shown here just the values between a growth rate of 0.5 and 3.5. If you start increasing it above 3.5, then you start to see much more variability in those patterns, and you get a sort of deterministic chaos. You get these bifurcations and strange attractors. In this case here, we're projecting the model 1,000 times, and you'll see that you always get, every time you run the model, you get the same growth curve, the same increase in population size. When the growth rate is up to about 3, then you get this bifurcation, which represents that the population could be either higher or lower, depending on which part of that oscillating system it eventually ends up at. And you get a series of subsequent bifurcations until at levels of above about 3.57, I think it is, you can get as your final sort of predicted population size after, I think this is run for 100 generations, you can end up with a suite of population predictions across the whole range of possible population size. And that's just from a very simple equation. Now, if you imagine the systems you're dealing with are assemblages of interacting populations with interactive dynamics. Now, if you look at the finer structure of these, you'll see that there remains a structure. And these are the sort of chaotic fractal dynamics that were very trendy about 15, 20 years ago, I think. But what this means is that even our simple equations, under certain conditions, lead to dynamics that are extremely difficult to predict. And so this nonlinear dynamic behavior is one of our key sort of elements of our difficulties and presents a limit to our abilities to predict. And that's illustrated here, where a very, very small change in initial population eventually leads to a sort of divergence of the dynamics of two populations that start virtually identical in terms of their initial conditions. And this means that when the present determines, as Konrad Lorenz said, when the present determines the future, but the approximate present doesn't approximately determine the future, then you need an absolutely precise ability to measure current conditions to predict long-term future conditions under these kinds of dynamics. And so there is an inherent almost impossibility to predict the dynamics of some of these kinds of systems. And that was a sort of dynamic of the butterfly, which hasn't worked out. But essentially, Lorenz's sort of metaphor, which became famous, was that a butterfly flapping its wings, which slightly alters a dynamic atmospheric condition, can, after a large amount of time, have resulted in a divergence that you couldn't possibly attribute back to its source. So the history is hidden. By studying the present dynamics, it's very difficult to understand what the initial conditions that led to current dynamics were. And when you think about this in terms of applying it to, even again, we're looking at a fairly simple system here. This single species dynamics, fish stock recruitment relationships. Analysis of what's been done so far, looking at a meta-analysis of all fish species for which there's good stock recruitment data. Philippe Curie and colleagues' paper a couple of years ago in Oceanography looked at just how little of the variance is explained by stock recruitment relationships. And yet this is one of the sort of central relationships that we've now been studying for 100 years. And we still are not really able to predict future stock size from current spawning stock biomass or future recruitment into a fishery. And another paper by Sarah Glazer and colleagues sort of concluded that, as looking at the dynamics of these systems, that fish species are more likely to display the kind of nonlinear dynamics implied in sort of maze simple models than fished ones. Dynamics are predictable over short periods, so the forecasting kind of range, in 70% of the 206 fish stocks that she and her colleagues looked at. But that predictability declines exponentially over a 5-year time series. And so the ability to make predictions, her overall conclusion was that the ability to make predictions in fishery systems is therefore extremely limited. And talking to people involved in the Alaska salmon fishery, one of the best studied fisheries in the world, for which some of the most complete data out there are available, it's still not really possible to forecast the strength of future salmon runs from the available information. So, prediction about the future is indeed difficult, even when we're looking at just one component of the oceanic system. Attempts to make these kinds of predictions based on a sort of simplification of those dynamics can sort of lead to sensational conclusions and sort of controversial subsequent discussions. And this was really an example, not so much of a prediction as an extrapolation of past trends of, even if you agree with the data here, of a large number of marine taxa exploited species in particular, which are sort of decreasing, or the percentage of collapsed taxa across a number of different taxonomic groups. And extrapolating from this projection, the authors, or at least those in the media who wrote about their work, were predicting the total end through extinction, commercial extinction of fisheries by the year 2048, which is not so far in the future. So I think Andre will pick up on this paper in his talk, so I won't say too more about it, but you know, that was a prediction or an extrapolation which was interpreted as a prediction by many in the media. So, you know, being careful about the use of the words sort of projection, prediction, scenario, etc., is a lesson for us, I think, in expressing the uncertainties that we have, being honest and transparent about that, but also trying to be clear with people about, you know, what our limits of prediction are is a key part of being effective in using our science for public policy. And just to sort of slightly confound that prediction, you know, there have been some notable recoveries in fisheries, even in places that are often maligned, certainly by my US West Coast colleagues, as being not well managed, like European Union fisheries. There's been successful recovery in stocks there. And really what that illustrates from the previous graphic is that an extrapolation of a past trend that does not take any feedback in the system into account is doomed to be an incorrect prediction, because we don't just stand by and watch systems completely collapse without some form of action or intervention. And understanding what that action or intervention might be is what allows us to talk about potential for recovery or change in trajectory of systems through our management action, some of the sort of governance grand challenge that we heard about earlier. And it was possible for the European Union, reaching crisis point in the biomass of fish species, falling well below what are thought to be sort of safe limits for spawning stock biomass. The closure of those fisheries and recovery plans has enabled them to successfully recover. So understanding and looking at trends in variables like, you know, spawning stock biomass, even though you can't predict the dynamics, is useful in terms of broad-based management recovery plans. And again, I think this is something that Andre will talk more about in his talk. So we can do a certain amount with models and predictions in fisheries despite the great uncertainties in the data. What about predicting the impacts of future climate in the oceans? The new climate models and the new emissions scenarios are of greater complexity. They have finer mechanistic understanding of the underlying physics, chemistry and ecology of climate change and its impacts. In this case, just looking at the sort of climatology of it, the climate models are better parameterized, but they haven't led to a reduction in uncertainty. If you look at the range of predicted future climates from the socioeconomic, special report on emissions scenarios, the SRES scenarios that were used in the first few IPCC reports, there's a range of projections for different scenarios of future emissions, and I'll come to scenarios in a second. But the more recent models, based on the representative concentration profiles of greenhouse gases, actually lead to a wider range of predicted possible climate futures. So better models, better data, no reduction in predictive capacity, essentially, which is kind of an interesting thing to think about. So more complex models and better understanding isn't leading to more precise predictions, and that was the conclusion of a paper published a few years back in Nature, which looked at the surprising stability in our predictions of what would happen to the climate when you doubled atmospheric CO2. So theoretical predictions from the early part of the century and from the mid-1950s are within the range of the predictions that are being made by our most sophisticated global circulation models right now. And we haven't reduced the uncertainty of our estimates from a sort of theory-driven look to a sort of much more complex dynamic system approach. So again, this is the authors of this paper sort of argue that we should acknowledge that we might have reached, when it comes to climate models, the limits of prediction. And that the time that we start thinking of, we know which direction things are going in. We don't know quite how much and how fast, and we will never know to a perfect degree. So that we should switch our time and effort into understanding the mechanisms, to deepening our understanding of the responses of the systems to this uncertain future change, and to preparing for those uncertain futures, rather than investing in, trying to increase our predictive skill. I think there is, from perhaps the sort of confidence that we have in mathematics and physics as predictive sciences, the view that climate models are these sort of sophisticated predictive, projective instruments that are essentially driven. And when you work, as I do often, in end-to-end models of the system, we often think of the system as starting with physics. But if you think about all those climate projections, including the representative concentration profiles, they start actually from scenarios about how much greenhouse gases we're going to emit. And in order to understand that, that's not a chemistry problem. There is chemistry in it. But emissions depends on how we think our economies and societies are going to evolve. And that's a very different process to try and understand those variables, to think about the prediction of how our societies are going to change. Now think about your lifetimes and the things that you have found surprising during that time. And the statements about, for example, technology that people, I can't remember who it was, one of the sort of founding fathers of the sort of computer industry said, I can't see what use anyone would have for a computer in their home. And those predictions are repeatedly confounded. People's predictions, not so much about just technology, but about the technology-science interface and the political responses of societies to changing conditions, are extremely difficult to predict. And yet it's these things and the complex and subtle and nuanced understanding of how society and politics works that in fact drives all your predictive models of future climate change. You put them through, you use this kind of stuff as input into your biophysical models, your GCMs and your shelf C models and so on, but underlying the projection of them is qualitative understanding of how society works. So I would say that social science, in fact, social science understanding drives our ability to understand and prepare for future climate change to a much greater extent than we perhaps acknowledge. And that's why it's so encouraging to see that integration within IMBeR. So just to focus briefly on what is in these emissions scenarios, what's behind the storylines, they're projections of economic futures. So there's a quantitative modeling component to economic forecasting, and we all know how reliable or unreliable those are. But there are also human population projections and guesses or best informed analyses based on past trends and future possibilities about how new and more efficient technologies might evolve. And, these projections are themselves, of course, subject to continual feedback. As the system changes, then some of the incentives and opportunities arise that we might not have predicted in advance. So, the scenarios have to be continually updated and changed. And that process is still ongoing within the IPCC for the next generation of scenarios. We have these sort of representative concentration programs, but they're still based on evolving scenarios that have not yet been published, still somewhat grounded in these original ones. But you've got these different storylines, and some of you are familiar with these. You've got different possibilities of, will the world be sort of more globalized or more regionally heterogeneous? Will countries go their own way? We have the Paris Agreement versus not being in the Paris Agreement. on emissions, for example. Those kinds of dynamics drive this. And will the world converge around a set of social goals, or will we see a divergence? The increasing inequalities, social inequalities that we've seen described by Thomas Piketty's book Capital, for example. So there's a lot of sort of social and political analysis that goes into your climate models. And I think, sort of message for that from IMBeR is that when you're, many of us are natural sciences. I think Eric's introduction of me didn't really highlight the fact that for the past 20-odd years, 30 years, I've been working largely in social science institutes. So although my original degree is in marine biologist, I think Eric's the first person since my mother to still think that I'm a marine biologist. But that's all right. He did say started, it's true. But yeah, so it's... When working with social scientists, I think they want to be involved at the start in the conceptualization of your models and your thinking about the future and about the potential pathways. I think there is a feeling sometimes that social scientists sort of come at the end and you present them with your sort of scenarios or models for the future and say, hey, this is the kind of impact that we're projecting. How are you going to help us communicate this to make it acceptable to the public or whatever? That's the role of communication scientists and others is at that end, but social scientists have kind of theories, models, projections, predictions, and interests in sort of driving the research agenda just as much as any biophysical scientist does. So take that opportunity here at IMBeR to develop joint research programs and questions with people from different disciplines. Okay, so predicting ocean change and its impact on society. If you look at the latest IPCC assessment, so this is a consensus statement. There's been a lot of research since this, of course, but on the basis of the consensus, all the sectors of the blue economy that are based on living marine resources, an interest for many of us here, they're all predicated to be negatively impacted under what we think of as the most likely scenarios for how anthropogenic global environmental change is going to unfold. And indeed, we have confidence that these sectors are already being impacted by change that has taken place to date. And, there's a level of confidence in those effects. It varies from being very high to being rather low. And, that's the case for many societal impacts, that our confidence is not as high as it might be in the projections of some of our physical and chemical changes that we're expected to see. So just to illustrate how IPCC decides what we know about climate change impact, it uses this sort of evaluation of evidence and the degree to which the evidence is of high quality and consistent, and what level of agreement there is on the direction and magnitude of the observed effects. And so it uses this sort of matrix to develop the confidence scale that I just showed on that previous slide. And just an illustration using ocean acidification, where there's a very high confidence that increases in atmospheric CO2 are leading to a decrease in the pH of the oceans. That's a very well worked out relationship. We can be certain that that will happen. In terms of biogeochemical processes, we have high confidence that that will have an impact. It will change, biogeochemical cycles within the ocean, and it will have impacts on the biology of organisms. Now, when it comes to what direction and magnitude of impacts how will they manifest themselves at the ecosystem level, we're only mediumly sure about what those things might look like. Largely, we're concerned about them. The loss of calcifying organisms, loss of fitness of calcifying organisms, for example. At the level of then how those ecosystems are used, what will that mean for the nature and type and value of provisioning services from the ocean and other regulatory and supporting services? We're pretty low confidence on what that will look like. And what those changes in ecosystem services will do to us as a society, well, anyone's guess. Okay, so the general pattern of almost any climate variable that you look at is something like this. There's certainty in the physical and chemical processes, or a level of understanding of what those mechanistic relationships are. But when it comes to predicting what the implications of those are for ecology and society, it becomes much more uncertain. Returning to a physical variable that is somewhat predictable, but even there has a level of difficulty in terms of projecting it. And remember, it's all driven by how good are those scenarios of how the future will unfold. But looking here at Bangladesh, heavily populated areas in the darker green there, and areas that are likely to be affected by flood, and the sort of magnitude of that. And that can really give us an impression that enables us to make decisions about future land management. And some of those decisions are relatively easy, but some are surprisingly complicated. So if you're faced with a map like that, and you've got certain decisions about whether to build sea defences or not, and how to manage the low-lying land behind those sea defences, you've then got complex social dynamics on top of that. And a lot of my kind of work has been in places like this, talking to people like these people working in this context. And at this level, people are making decisions based on resource availability and opportunity. So in a lot of coastal low-lying Asia, you've got a dilemma of whether to use that low-lying coastal land to farm rice or shrimp. If it's becoming salinated and gets flooded with seawater often, and the quality of the land decreases, then you might think about going for shrimp farming versus rice. But if you look at the dynamics within a community and within a place, such as coastal Bangladesh or coastal Vietnam, it's the wealthy people that have fish ponds, that have prawn farming businesses for export, and it's the poorer people who farm rice. So the decision as to whether to open a bund and to flood an area with saline water to grow shrimp is one that's taken in the midst of village dynamics, power relations, and a whole bunch of local politics. So understanding that is something that you also need to take on board when thinking about how the system will evolve. And then there are feedbacks from how you manage this land, the amount of greenhouse gases it will emit for a start, into understanding the climate system. So the decisions of people, rich shrimp farmers, to deliberately break coastal defenses to let saline water flood land and crowd out rice farmers, those kinds of decisions influence our future emissions when multiplied several hundreds of thousands of times. And it's those kinds of things that mean that predicting the responses of social ecological systems is really difficult. But understanding the mechanisms which the various parts of the system respond by is still a worthwhile thing to do. So I mentioned that I do some global end-to-end models, and I was reflecting that we don't, in our modeling exercises, think enough about those limits to prediction. This is some work I'm doing with Harvard Institute of Public Health and a bunch of others, UBC and so on, which basically looks at changing marine environmental conditions, sea surface temperature change, other climate variables, leading to shifts in the distribution and abundance, productivity of fish populations that are exploited, therefore of catches in the future, therefore of fish available for consumption. And there's a sort of mechanistic model at each interface between these to try and explain and quantify some of the feedbacks between them, to eventually human nutrition, and then eventually outcomes in terms of human health. So we've done some preliminary work on this, and it was published last year. And, against the background of fish as an important source of micronutrients and widespread deficiency of particular micronutrients. So a third of the global population is vitamin A deficient, for example, and certain fish are vitamin A rich. The rich part of the vitamin A is mostly contained in the eye, by the way, so eat your fish with a head on, and including the eye if you want to get the full nutrient benefit. Zinc deficiency and iron deficiency, fish can also be good sources of these. Now, those of us who are well-fed get our zinc and iron and vitamin A from a whole range of things. Those with more limited diets, fish can be a really important source. So we figured out where those places are, which populations are vulnerable to becoming deficient in at least one of these nutrients by 2050, under projected impacts of climate change, business as usual fishery management, and various other scenarios of fishery management, and various extrapolated trends for aquaculture growth. And, you know, so there's a lot of assumptions built into a projection of this kind, and it's very difficult to sort of begin to put confidence limits on it. The best you can do is some kind of sensitivity analysis and report some of the range of outcomes that you get. Something I think we rather neglected to do in this paper in our rush, as you do in these kinds of journals, to publish a nice coloured map. And so climate-related changes in capture fisheries here affect those populations most dependent on fish, most dependent on vulnerable, and most vulnerable to micronutrient deficiencies. You map the distribution of micronutrient deficiencies, the changing productivity of the fish in the blue colours in the EEZs, and you pinpoint the countries that are dependent most on fish as a source of these micronutrients, and figure out where it matters most that climate change will be impacting the availability of fish in people's diets. And you know, you could keep adding feedbacks and potential responses in parts of the system. Cultural feedbacks are largely missing from here. You know, are people's tastes evolving away from eating whole small pelagic fish, as they are in some West African countries where it's kind of uncool? It's your grandparents' food, you know, small pelagic fish. You want to eat something that's kind of more modern. And, you know, you have all of these dynamics which are not built into this. But nevertheless, we can use this as a means to say that, you know, fish is an important part of the global food system. There's a nutrition concern for the impacts of climate change. And this is part of this evolving field of planetary health that looks at the links between climate change and human health in various forms, from changes in epidemic diseases to the shifting nutrient content of terrestrial crops as a result of climate change. So, you know, there's potentials to think about predictions and projections also for this public health field. Many of the predictions that we see are filtered through economics, and the Stern Review was sort of a very prominent publication that I think got a lot of the business community and governments really, it revealed the potential impacts in ways that those communities could really understand. So here, projections of economic value based on a whole range of assumptions were extremely valuable in changing action. So, you know, you've heard the phrase self-fulfilling prophecy. If you can get a credible analysis of what might happen if you don't do anything, and that don't do anything scenario is sufficiently serious for people to take action, then it's more likely that they will change, that they will take action. So that in itself becomes a prediction of a future likelihood of a socioeconomic scenario. So you need to think about the sort of coupling of these feedbacks and how, you know, your science can affect future emissions by the way that it enters the public and the political discourse. But economics is not the only social science, and one of the things that I've tried to sort of bring people's attention to is that there's a huge literature and some important thinking about climate change in fields like anthropology, political science, and psychology. And understanding and using those sciences alongside and in our sort of communication of our science is something that we have an opportunity to do in IMBeR. I think we have anthropologists. Here we have political scientists. I'm not sure, I don't know if we have any psychologists, but any psychologists? No? There we go. We've got a missing group of social science humanities scholars that we might want to engage with. Oops. So I've looked at the uncertainties in the sort of biophysical science. To what extent can we predict some of the big social drivers that are in those SRES scenarios and underlying those concentration pathway analyses? Are we any better at predicting the impacts of new technologies and, for example, social change than we are at predicting climate beyond a few weeks? The answer is probably no. Apart from The Simpsons and I think one professorial pundit, nobody predicted the outcome of the last US presidential election correctly. So there are limits to prediction, even based on extensive polling data. We weren't able to sort of predict this outcome, but the TV show The Simpsons did, of course. So qualitative prediction is sometimes more reliable, arguably. Although, you know, one prediction among millions is just a chance stochastic event, I would suggest. But the ocean is going to evolve in ways that we can barely imagine. And what's missing often from our predictions and even our scenarios is the ability to anticipate the unknown. We tend to, when we think of prediction, we're largely extrapolating from past experience. Unconsciously, we begin to call it projection, prediction, but those terms are not really fully accurate if they don't take into account the possibility of things that we struggle to imagine from past experience. And it's useful taking a look at sort of past utopian visions and seeing, one, how they influence the future, but also you know, how to assess their sort of credibility and likely impact. And there's a lot happening at sea these days. You get visions of cities like these, techno-utopias. You get the whole arena of climate mitigation, technological fixes in geo-engineering. And some of this might have looked like science fiction some time back, but you know, people are seriously considering these as ways to address our future climate change burden. Political and social solutions, reducing consumption, signing up to emissions limits, etc., having either failed or being potentially too slow to address dangerous climate change. So people are looking to technical solutions as well. Food from the sea in the future might not just be seafood. This will change the agricultural emissions. And one of the things that I think is possibly missing from future scenarios of climate change is if you look at the concentration pathways and emissions projections, they take into account changes in land use. And at the moment, I don't think they do anything much with the sea. The only thing that I've seen mentioned in the latest IPCC report is the impacts that shipping has on future emissions. And the way that we use the oceans might have an impact on the carbon budgets and the ocean-atmosphere interactions in ways that are not being perhaps incorporated into these models, as far as I can tell, and people may correct me on that one, in the way that the land use change data is being very centrally used to drive future emissions scenarios. A couple more sort of futuristic projections. Renewable energy from the sea is potentially one of the sort of big game changers, and you know, we're starting to see large infrastructure in the sea and shifting property rights to accommodate that, and changing conception of what the oceans look like towards much more of a sort of marine spatial planning that looks like land use planning. I'll use this, try and get this to respond faster. Ah, okay. Whoa, that was too fast. Okay, I just have one or two slides left, I think, but it's that one. So we're starting to see the future come true very, very quickly. Quicker than this slide. Huge offshore energy solar farms in China that are transforming the way that we generate energy and the way that we use the sea. Maritime transportation, you know, these are futuristic images of solar sails that will cut fuel consumption of this sort of major transportation sector. That's already coming true, however. That's a ferry in Hong Kong which has solar sails. And one of the insights from another of the social sciences that can help drive behavior, and it's behavior that drives our emission scenarios in the end, is that projections of doom and images of doom, getting people engaged and interested in taking actions is not going to work through fear alone. And I think we've tended to, particularly ecologists among us, have tended to use fear as a sort of motivation for public action. And there's been a number of studies that simply say, well, fear won't do it. Seeing images like this makes you feel helpless, sad, angry, but it doesn't make you engage in positive action. Whereas more positive, non-threatening images that relate to everyday emotions and concerns, you know, family, the future, children, making the immediate environment around us more pleasant, those kinds of images can help catalyze action. And there's also another series of studies that show if you get people engaged in local climate action, trivial and meaningless as it may appear to a modeler looking at global biogeochemical cycles, what is significant is that people who are engaged in this kind of thing tend to align their voting with policies that support green technologies, emissions reductions, and so on. So there's, you know, there are linkages between these things that there is empirical evidence that these linkages lead in the end, or could lead to emissions reductions. But we're a long way from getting action on climate change at a significant level among large sections of the population. This European study of public awareness and concerns and priorities about anthropogenic change in the oceans overwhelmingly is concerned about pollution and somewhat with fish stocks and overfishing, coastal erosion and so on, but not so much about climate change. So there's still concerns. The oceans tend to be left out of climate change discussions. So that's a sort of overview of where we are with limits to prediction across a sort of range of domains that I hope shows you the sort of interlinkages that we're dealing with and that allow us to explore, I think, exciting mechanistic modeling around you know, simulations of what if people change their behavior, what if this happened. I think that provides us with a series of opportunities that we haven't perhaps fully taken yet. So some questions to leave you with, really. We often hear this refrain, we need more data. So my question would be, is it lack of data that's hindering our predictive ability, even today in the age of big data? Is that the constraint? Regarding irreducible uncertainties, is the complexity of the systems that we're dealing with a limit to its predictability? And therefore, you know, do we need to sort of engage our efforts in something other than increasing predictability? Does better understanding lead to better prediction? Some of the analysis that's emerging suggests not, but you know, there may be counterexamples. Do better predictions result in better actions? Again, here, this is an area that we perhaps haven't looked at that much. If we have a good idea of what's going to happen, does that mean that that spurs people into action? Well, there's a lot goes on between the presentation of facts and the interpretation of those facts, as we know, and the action based on that. So what are there alternatives to that logic? And it's the logic that we as researchers, as scientists, as rational thinkers, we like to think, our logic is more data, better predictions, more effective actions. That's the kind of justifying logic. If you read any climate paper, it usually starts something with some statement that encompasses that sentiment. Are there alternatives to that logic? Will improved understanding of what it takes to change course, or creating a more compelling vision of alternatives, or being better prepared for the unpredictable, are those things that we should be directing our research attention to a greater extent? So those are the questions that I leave for Workshop 1 and for the group as a whole. Thanks very much.
Okay. Thanks, Eddie, for a very provocative and stimulating talk. Lots to think about over the week. So do we have some questions? Follow-up comments?
So wait for the microphone. This is
I still don't need a microphone. Andre Pant, you've talked about prediction, but prediction means that you're starting from somewhere. And so I guess from a fisheries point of view, I've said in public fora, embarrass myself, but by saying a good estimate of fish population size is half to double of the true value. If you don't know where you are, how can you predict, how can you even think of making a prediction?
I agree with you. Fishery scientists, may think differently to that. I think you project from where you think you are as best you can, and that's often what we're doing rather than making a prediction. As you correctly point out, I think in order to make a prediction, you have to know your starting position. And I think that I had a couple of slides sort of, agreeing with that proposition of saying that, prediction, and I think a lot of those statements about the difficulties of prediction relate to that inability to know your starting point with the precision necessary to make a prediction in a system that is dominated by complex nonlinear dynamics. Now, if the system is less dominated by those, then a rough knowledge of an approximate knowledge of your starting point will give you an approximate knowledge of the future. It really depends on the extent that the system is dominated by these sort of complex nonlinear dynamics. Now, I have heard it read, I've seen papers with the title of, Mother Nature as a strange attractor, that we may not have that sort of unconstrained variability that's implied by the sort of simple nonlinear models, that the parameter values necessary to create those chaotic dynamics may not happen because of dampening feedbacks. Now, I am not current enough with the ecological literature to know where the thinking is on that, and that would be a sort of fun thing to think through. I don't know, Andre, if you have any particular sort of sense of that, or whether others in the room do. Probably a workshop question.
Hi, Eddie. Jason Link, NOAA Fisheries. Let me underline fisheries for you. One of the things you kind of left us with is why should we even bother to make predictions? You were being provocative. Let me ask you this question. There are other approaches and tools to making predictions that help deal with some of that uncertainty. I wonder if you could speak to that. For example, looking at hierarchy theory and emergent features, looking at multi-model ensembles, the way we use in hurricanes, et cetera. So I wonder if you could bring us back from total hopelessness of being able to predict anything.
Yeah.
Thank you.
No, and that's, Jason, that's exactly the reaction I hoped for from this community. And, I know there are Bayesians out there among you, for example, and others who have very sophisticated tools for addressing how you deal with uncertainty in prediction and give us bounded future uncertainties. And I think, scenarios, hierarchy models, Bayesian approaches and others, I think, help to bound what might seem as sort of limitless uncertainty into domains of uncertainty that we can grapple with, that we can understand and that we can respond to, and we can say, okay, we don't know exactly how things are going to work out, but we think it's going to be like this and like this, between this and this, but we might be surprised, and we're prepared to accept the risk of being surprised and act anyway. And it's somehow communicating that seems to be the sort of central challenge. And I think, anyone that sort of tries to, people who are hostile will always use those kinds of statements of uncertainty as a way to stop you getting any credibility from them and action from them. But I think people who consider them seriously, and that includes people like the banking industry, the insurance industry, the mayors of major cities, all of these people are taking the predictions that some of your work on sea level rise, on sort of global change is producing, and making serious commitments of finance and of policy based on them. So I painted a somewhat hopeless picture at a sort of more conceptual level, but at a practical level, I think we do have the tools to make good use of the science. And I think it does sort of play to this idea that if we have a good mechanistic understanding, then we can accept and get a better sense of what our uncertainties are. I think if we head too much down the prediction route and don't embrace a fuzzier approach, a more qualitative, a more bounded scenario approach, then we risk being taken for false prophets.
Hi, this is Charlie Stockham from NOAA's Geophysical Fluid Dynamics Lab. I guess the two quick comments. The first is, you bring out the example of our inability to sort of close the bounds of uncertainty on global temperature, and I think that's very much true. The counter argument to that, of course, is that the present uncertainty bounds on that quantity have already done a great job sort of informing global decisions about our future forward. So there's a question of whether the precision is good enough to answer the key question at hand. And in that case, I would argue that on a global scale, that's had some success. I think where some of the challenges lie is translating that to sort of regional scales and time scales at which the decisions need to be made. And there I would argue that there has been some progress in terms of regional and, say, multi-annual time scales in addition to the century scales, but there's still much more progress to be had. So I guess if you have some thoughts on that, it would be good to hear.
Yeah, I think the downscaling experience has been very mixed, and it really depends on the variable. Sea surface temperature, air temperature, sea level rise, those kinds of parameters, I think, have been very effectively projected at scales, and the differences between regions have been sort of shown quite convincingly with reasonably bounded levels of uncertainty. When it comes to some of the others, precipitations, I mean, somebody mentioned, I think, ensemble models earlier, and I do some work in the Mekong, and depending on which model you take, in the regionally downscaled ones, they can predict either an increase or a decrease in precipitation. So if you're trying to then plan for balancing hydropower development with fisheries with irrigated rice on the Mekong, and your climate change scenarios are telling you that rainfall into the Mekong Basin could either increase or decrease under climate change. It's not going to stay the same. But it'll do one or the other, or it might stay the same. It's within the bounds of the average of the ensemble models. So, in that case, it's possibly not yet useful, but you know that you're likely to face some kind of change, but you're not quite sure what. You can act to a certain degree on that, but I think where the change is at least directional, again, decisions about how high a seawall you build or how far you retreat from a coast in planning your future infrastructure growth. Those require a degree of predictive ability, and I think, we are committed to trying to provide that sort of predictive ability. But in terms of the dynamics of the ecological world, it's probably, I don't know, I would struggle with providing a sense of where we go. I think we use some deterministic models, for example, on fish physiology to drive where we think fish will be in the future based on their temperature and oxygen tolerance and things like that. But there's a lot of other biology going on that we don't know how that will play out. So I think projecting where fish will be in the future based on an understanding just of their physiology might be problematic. And I work a lot with William Chung and others who do that work, and it's in some of the papers that I've co-authored. So I'm not down on it. I'm just I worry about its again its limits to the limits of its utility. So I think it is a complex area, and one that I think we need a dialogue with decision makers about how to deal with that.
I think we have to break out for coffee. Thanks again, Eddie. I guess